Today on Macaulay Math, we're solving logarithmic equations. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 14 on solving logarithmic equations. Our goals for today. We're going to solve simple exponential and logarithmic equations. We're going to solve complex exponential and logarithmic equations. And we're going to use exponential equations to model data and solve problems. In this lesson, we get to the work of solving logarithmic equations where the unknown quantities are either an exponent or part of a logarithmic equation. By using both the definition of logarithms and the properties of logarithms from the previous lesson as tools, solving these types of equations becomes a rather simple task. Let's get started. Okay, when solving equations involving exponential variables or logarithms, we're going to make sure that we're following the rules of algebra, especially order of operations, because logarithms are going to be on the same level as exponents. We'll use the definition of logarithms to convert to exponential form when we can, and use the last property of logarithms. Now, when I say last property, I'm talking about from the last lesson. We'll use that last property that allows us to take the exponential of a logarithm and bring it down there in front. So other than that, we just have some examples. So let's start with some easy ones. And the first one we'll start with: solve the following equations without a calculator, and you'll see we have 3 to the x is equal to 81, and the only way that I can do that without using a calculator is if 81 is a perfect power of 3. And it turns out that 81 is equal to 3 to the 4th power. So if I go 3 to the x is equal to 3 to the 4th, clearly if the bases are the same, then the exponents have to be the same, so x is equal to 4. All right. Similarly, we can do this a number of ways. The first thing that I am going to do is I am going to say that I'm going to use the property of exponents that says if I have a base to a negative exponent, I can rewrite that as 1 over the base to the positive exponent. And I'm going to do that in reverse. So technically, there's a 1 right here. And so if I use this property in reverse, I can rewrite this as 2 to the negative 1 to the x power is equal to 32. And then I'll get rid of my parentheses here by using the power to a power rule. A to the x to the y is equal to a to the x times y. And that's an easy multiplication. Negative 1 times x is negative x, so I have 2 to the negative x is equal to 32. And just like the previous example, the only way that these two things can be equal is if 32 is a perfect power of 2, and it turns out that 32 is 2 to the 5th power. So I have 2 to the negative x is equal to 2 to the 5th. Since my bases are now the same, I can set the exponents equal to each other, so I've got negative x is equal to 5, and from that we can conclude that if negative x is equal to positive 5, then positive x is equal to negative 5, and that is our final answer for that one. All right, next, solve the following. Now, we are going to need to use a calculator to solve these, especially since we know that e is an irrational number. Now, when we're using e, I would always suggest that we use ln. So for the first thing that I'm going to say here, I'm going to say take the ln of both sides. And the ln of e to the x is equal to the ln of 66. Now I'm going to use the property of logarithms that say log base a of x to the n is equal to n times log base a of x. And I'm going to do this, and then we're going to talk about a shortcut here real quick. If I bring this down, I'll have x times the ln of e is equal to the ln of 66. And if you will recall, the ln of e is always equal to 1. And so I'll just have x equals the ln of 66. Now that is fine as it is, or you can go to decimals with this. And I will type in the ln of 66, and I'll get 4.1896. So if I'm rounding in 3 places, I'll round that up, which will round that one up. So I got 4.190. Either of these is acceptable. But I do want to say one thing. From this point on, if you have ln of e to a power, you can skip this step and just say, okay, this cancels out and I'm left with just x. So ln e to the x is always going to be just x. That is a property that came from the first lesson on logarithms, but you can use it from this point on. All right, let's solve this for x. Okay, so I said in the beginning that you definitely want to follow your order of operations. So before I can bring this exponent down using that property of logarithm, I have to move the 5 that is multiplied to the exponential first. So using my order of operations, I am going to divide both sides by 5 first. And I do that so that I can use that property of logarithms right here. When you bring that value down, the exponential has to be by itself. I'm going to divide both sides by 5. Those cancel. 8 to the x. And it turns out that when you divide 325 by 5, you are left with 65. 5 goes into 30 6 times. 5 goes into 25 5 times. Here, you can take a known logarithm of both sides. I'm going to use ln. Now, because the base of this exponent is not e, notice we had an e here, the ln of e canceled out. Because the base of this logarithm is e, this ln and this 8 does not cancel out. So I still have to use that property of logarithms. Log base a of x to the n is equal to n times log base a of x. Now, in that last one, ln e canceled out, and I was done. This one, the ln of 8 is not 1. It doesn't cancel, but I can put it in the calculator. It's just a number. So in this case, I am going to divide by the ln of 8. Those will cancel. I'm left with x equals. Now this is going to be an irrational number, and that's okay, but we'll go right to decimals and we'll just type that in. ln of 65, hit your backslash, ln of 8 gives us 2.007. 2.007. Okay, next bunch. Solve the following. Now, this first one looks like a challenging problem, but if you use the property log base a of x equals log base a of y, if and only if x and y are equal, then here I'm going to say add the ln of 2 to both sides. That'll give me the ln of x is equal to the ln of 2. Since the logarithms are equal and the logarithms have the same base, the only way that that can be true is if what you're taking in the logarithm is equal. So x has to equal 2, and we are done with that one. All right, the next one here, you'll notice there is only one logarithm here. There is no logarithm over here. So I can't use this property that I used in the last one, but I am going to use the definition of logarithm. And I'm going to change this to an exponential. And that will give me x squared is equal to 81. Here I'll just take the square root of both sides. Now normally when you take the square root, you add plus or minus to it. Now that'll give me x squared is equal to plus or minus 9. But, just as a note, the base of a logarithm must be positive. And you'll notice that x, what we're trying to solve for right here, that is a base. So we're going to get rid of that. So my final answer is just going to be x is equal to 9. All right, last page. Solve the following. Once again, this one's different than the last one, but more similar to this problem right here. They give you that both of these logarithms on either side of the equation have the same base. So we can use that property, log base a of x equal to log base a of y, if and only if x is equal to y. So right off the bat, since the bases of the logarithms are the same, what goes inside the logarithms must be equal. Solving for x, let's subtract x from both sides, minus x, that gives me 4 is equal to just x, so x equals 4. All right, now I want to get it to be something that looks like that last example, where I have one logarithm on the left, one logarithm on the right with the same base. But I have two, I have this subtraction. So we're going to use that property of logarithms from the last lesson that says log base a of x over y is equal to log base a of x minus log base a of y. But we're going to use it in reverse. Since I have a subtraction, and I have a subtraction here, I can combine these with a division. So we'll have the ln of x plus 1 over x minus 2 is equal to the ln of just x. So now, just like in the last one, I have two logarithms with the same base, so we will use log base a of x equals log base a of y if and only if x is equal to y. And we'll say x plus 1 over x minus 2 is equal to just x. Here, I want to solve that for x. I'm going to end up with a quadratic. So the first thing I'm going to do is I'm going to multiply by x minus 2. So if I multiply this whole thing by x minus 2, on the left-hand side, the x minus 2's cancel, so I have x plus 1. I have x times x minus 2. Here I'm just going to distribute. And that'll give me x plus 1 equal to x squared minus 2x. And if I move all of the terms to the right, I get 0 is equal to x squared minus 3x minus 1. And for this one, I have to use the quadratic formula. And the reason that is because when I look at this, I go, okay, are there two factors of -1 that add up to -3? And the answer to that is obviously no. That doesn't mean that it doesn't have a solution. So I'm going to use the quadratic formula on this one. So I'll say x is equal, start with negative b. Since b is already -3, negative 3 becomes +3, plus or minus the square root of negative 3 squared. Remember, if you use the calculator to simplify this, you have to put the parentheses around the negative. Minus 4 times a. Well, a is the coefficient of the x squared, and that's just 1. And then c is the coefficient of the constant, which is negative 1. And then that is all over 2 times a, which is just 1 again. And this is fairly easy to simplify. I've got my 3 plus or minus. Negative 3 times negative 3 is 9. Negative 4 times negative 1 is positive 4. 9 and 4 is 13. And that's all over 2 times 1. Normally, I would say put a box around this and you're finished. That being said, let's go back up here to the original. This original has an x plus 1, x minus 2, and an x. Now, you are not allowed to put a negative number into a logarithm. I can put up to negative 1 into this logarithm. I can put up to 0 in this logarithm. And then the smallest that I can put into this logarithm is positive 2. When I come down here, the square root of 13, I don't know what that is exactly, but I do know that it's more than the square root of 9. The square root of 9 is 3. So when I do the negative here, 3 minus the square root of 13 will give me a negative value. And since it's a negative value already, when I subtract 2 from a negative value, that result will be negative, so I cannot take that as my final answer. So my final answer can only be the positive. And so that is our final answer. That is the exact answer. Now, we can always go ahead and check that. And we'll use Desmos just as a real quick check, just to show that I am right, that there are not 2 solutions, there is only one. If I go to Desmos and we type in that value, so 3 plus that is what we think our answer is. And then I can type in f of x is equal to ln of x plus 1 minus the ln of x minus 2. And then g of x is equal to just the ln of x. If I come here to where there's an intersection, we get 3.03, which is the rounded version, rounded to 3 decimal places of what we got there. So I'm fairly confident that this is my final correct answer. All right there, folks, that's all I got for today. So, Star Wars fun fact of the day. Mark Hamill and Carrie Fisher actually performed the swing across the Death Star chasm because there was no budget to cover stunt doubles. So they actually did it themselves. Way to go, Luke and Carrie. Well, that's all I got for today, folks. Have a great day. Goodbye.